spatial rotations in 3 dimensions can be parametrized using both Euler angles and unit quaternions. This article explains how to convert between the two representations. Actually, the simple use of quaternions was first presented by Euler some 70 years earlier than Hamilton to solve the problem of magic squares. For this reason, the dynamics community commonly refers to quaternions in this application as Euler parameters. Definition: a unit quaternion can be described as: we can associate a quaternion with a rotation around an axis by the following expression, where I plus or minus is a simple rotation angle and cos I squared x, cos I squared y, and cos I squared z are the direction cosines locating the axis of rotation. Rotation matrices. The orthogonal matrix corresponding to a clockwise left-handed rotation by the unit quaternion is given by the inhomogeneous expression, or equivalently, by the homogeneous expression. If is not a unit quaternion, then the homogeneous form is still a scalar multiple of a rotation matrix, while the inhomogeneous form is in general no longer an orthogonal matrix. This is why in numerical work the homogeneous form is to be preferred if distortion is to be avoided. The direction cosine matrix corresponding to a body 3-2-1 sequence with Euler angles is given by conversion. By combining the quaternion representations of the Euler rotations we get for the body 3-2-1 sequence, where the airplane first does your turn during taxiing on the runway, then pitches during takeoff, and finally rolls in the air. The resulting orientation of body 3-2-1 sequence is equivalent to that of Lab 1-2-3 sequence, where the airplane is rolled first, and then nosed up around the horizontal Lab y-axis, and finally rotated around the vertical Lab z-axis. Other rotation sequences use different conventions. For Euler angles we get arctan and arcsine have a result between ai/2 and i/2. With 3 rotations between ai/2 and i/2 you can't have all possible orientations. We need to replace the arctan by arctan2 to generate all the orientations. Relationship with Toita-O'Brien angles. Similarly for Euler angles, we use the Toita-O'Brien angles, roll a Euro rotation about the x-axis, pitch a Euro rotation about the y-axis, yaw a Euro rotation about the z-axis, where the x-axis points forward, y-axis to the right and z-axis downward, and in the example to follow the rotation occurs in the order yaw, pitch, roll. Singularities. One must be aware of singularities in the Euler angle parametrization when the pitch approaches a plus or minus 90 a degree. These cases must be handled specially. The common name for this situation is gimbal lock. Code to handle the singularities is derived on this site, www.euclideanspace.com. See also, rotation operator, quaternions and spatial rotation, Euler angles, rotation matrix. Rotation formalisms in 3 dimensions, external links, Q60. How do I convert Euler rotation angles to a quaternion? And related questions at the Matrix and Quaternions FAQ, references.